This is a refreshment for the electrocyclic last class what we saw. So first we should calculate the electron count from the system. If it is a 4N system, then the condition is thermal, the Kahn rotation is allowed. If the condition is photochemical, the disk rotation is allowed. So which isomer we are going to take, under which condition, what will form. So that is the whole concept in the electrocyclic things. So we are taking the same configurational isomers like ZZ or EE. Then we are subjected to Kahn rotation. You are end up with the trans cyclobutene product. If you are taking a different isomers like EZ or ZE, then you are subjected to Kahn rotation. You are getting a cis isomers. Same is true for the 4n+2 system also. So this is a summary of electrocyclic reactions. Now we are moved to the cycloaddition part. So start with that, the common one, 4+2 cycloaddition. There is new 2 sigma bonds are forming, one more pi bond is formed. Okay. So here the molecular orbital diagram of the diene and the dienophile. So this is the new sigma bond formed. This is the new pi bond forming. These two is the new sigma bonds. This is the transition state of the cycloadditions. So we are getting this product. Okay. Now classifications. So it depends upon what is the number means is. This is mostly mean to the dienes. This is mostly mean to the dienophile in the Diels order reactions. So here there is only ene only. Both are ethylene molecules. So this is 2 pi electrons, 2 pi electrons. So this cycloaddition is called as 2 pi 2 pi or 2+2 cycloadditions. This is a diene, this is a dienophile. So this is 4+2. Here 4 pi electrons are involved in the transition state. Here 2 pi electrons. So this is called 4+2. But this is 4+4. The larger 2 dienes can participate in the cycloadditions. It's called 4+4. Then this is 4+6. So here from the diene there is 4 pi electrons, and from the heptanone it's a 6 pi electrons are involving. So before coming to the cycloadditions part, we should know how we will approach. Here also molecular orbitals are involving. Here the new concept is a facial additions. So if a suprafacial addition, so this is the frontier orbital of diene. Then the dienophile is approaching in the same side of both of the frontier molecular orbitals. That is called suprafacial addition. If one orbital is approaching upward, one orbital is approaching downward, means that is called anterofacial. So this is an example of a suprafacial and suprafacial additions. So this is a molecular orbital diagram of a diene. So this is a HOMO level. This is the HOMO level. This is a LUMO level. This is 2 nodes are there, right? So here, this is as such, it's addition to the molecular orbital of the diene. So same side the addition is happening. So what we are focusing here is the addition. So I am not talking about how is the bonding interactions between this. Okay. First here also same like 3 methods are frontier orbital method, orbital correlation method, transition method. Orbital correlation method we already saw in the electrocyclic, right? Here also the same scenario, C2 plane, C2 axis, M2 plane. So many things will happen, but the concept you should understand. Okay, I'll start with frontier orbital method. So this is a alkene. So this is the ground state of alkene. So thermal condition, this is a normal molecular energy levels for the alkene. So this is the HOMO level of it. When we are subjecting to UV light, like photochemical conditions we are introducing, means one electron from here it will jump. So now this is the HOMO level. So in this one we should clear about in thermal conditions what is the HOMO level. 0 node is the HOMO level. In photochemical condition 1 node is the one node is the HOMO level. Okay. So suprafacial mode first. This one HOMO of 1 ethylene. So the bottom one is a HOMO of ethylene. This one under thermal conditions, right? So this is a HOMO. So HOMO of 1 ethylene we are taking here. Then LUMO of another ethylene. So this is a LUMO of another ethylene, both in the thermal state only. I am not talking about here. This is the photochemical stage. Leave it. So this is the thermal state. So 1 ethylene HOMO. This is another ethylene LUMO. So when these two are suprafacially approached, so one side it's forming a bonding interaction. So this is a bonding interaction, but here is not, right? So this is the anti-bonding one. So if you are getting both side bonding interactions, that interactions are allowed. Now you are getting one side only bonding interactions, either right side or left side, which means this is thermally not allowed, forbidden. When you are photochemical conditions there, so this is the HOMO level of a one alkene in a photochemical conditions. So this is a HOMO. Then this is a LUMO of unexcited ethylene. So when these two are close together, suprafacially approach each other. So this also forming a bonding interaction. This also forming a bonding interaction. When it's turned to anthrafacial mode, thermal will be allowed, photochemical will be not allowed. But the problem is geometrical. See, this is only two carbon system. So one can approach this phase, other can approach this phase is not possible by geometrically. Geometrically is not possible because only two carbon systems is, it might be a longer chain things, it may possible, but 2 plus 2 things, and even though the molecular orbitals can approach each other by anthrafacial, but it's geometrically unfavor, so it's very, very rare. Okay. Then is a 4 plus 2 cycloadditions one. So first I am taking a LUMO of diene and a HOMO of dienophile. Okay, this is a HOMO of a dienophile. This is the LUMO of a diene. So now it's a suprafacial interaction. Now you are getting a bonding interactions both sides. So this also bonding interaction, this also bonding interaction. So this can undergo 4 plus 2 cycloaddition under thermal conditions very quickly. So if I am taking reversely, like HOMO of a diene and LUMO of a dienophile, then both are end up with the same bonding interactions only. So 4 plus 2 additions under thermal conditions is very feasible. It will end up with the bonding interactions. Okay. When the photochemical conditions are there, now I am taking a HOMO of dienophile and LUMO of a diene. Now one side is the bonding interaction, but other side is not. It's anti-bonding interactions. There is no overlap between this. So if I am taking HOMO of a diene and LUMO of a dienophile, the same scenario repeated. So when you are comparing these two, 4 plus additions under photochemical condition is not possible. Not possible, it's not allowed, it's disfavored. But under thermal condition is possible. So it's allowed. Okay, so this is a table of this. So 4 end systems, which means 2 plus 2 thing. The supra conditions thermally is forbidden, but photochemically allowed. But anthrafacial additions thermally allowed, but the problem is what? Geometrically is unfavored. So mostly that anthrafacial interactions won't happen in the 2 plus 2 systems. Okay. Then 4n plus 2 systems, like 4 plus 2 cycloadditions. So suprafacial itself it's allowed, correct? But photochemically it's forbidden. Same it's reversed for the anthrafacial mode. So when anthrafacial interactions are there, thermally it's forbidden, but photochemically it's allowed. Okay. Now closely look into the 2 plus 2 cycloadditions. So which are the concerted thermal one. We saw just now 2 plus 2s are forbidden and rare. Okay. Such conditions symmetrically allowed only when the two pi systems approach a perpendicular manner, which means anthrafacial one. Anthrafacial is allowed, but the geometrically disfavored. There is a one exception. Always chemistry is living with exceptions. So the cycloaddition of ketene is one exception. We will see that one. When the photochemical one, suprafacial itself it's allowed. So the dimerization of cis and trans is also taken in the under photochemical conditions. Okay. So this one, the regioselectivity. So when these two double bonds, this undergo 2 plus 2 cycloadditions, under photochemical, this product is not forming. This product means only this product is forming. Why? If this product are formed means there is a diradical things. So this mechanism also is one more time verify that this is not undergoing ionic mechanism. If ionic mechanism means some intermediate will form, right? Some cations will form, some anions will form. So when we are subject these two into photochemically, we are not getting this product. There is no diion intermediates. So we are getting these products. Okay. If cis or are subjected to photochemical conditions, you are getting either cis syn cis or cis anti cis. So when the trans isomer of the butene is taken to the photochemical condition, you are getting either trans anti trans or cis anti cis. When mixture of these two um, unsaturated compounds are subjected into the photochemical conditions, we are getting all of these above compounds, because one cis isomer can dimerize with cis isomer, or one cis isomer can dimerize with trans isomer. Trans also can dimerize. So there is so many possibilities. So all of the above compounds will be formed. This is the only one excess one. Cis, syn, trans. That's all. Okay. So this is the same one, but there the substitution is only methyls. Here it's a phenyl one. That's all. So we are getting these things. Okay, the cross additions. When we are taking the cross additions, we are getting the crossed products. That's all. So here, this is the benzene ring. This is the benzene ring. This double bond is not conjugated with this both of the rings, correct? Because this is separated by one sp3 carbon. So here also is sp3 carbon. Here also is sp3 carbon. Now this double bond is sparked into the 2 plus 2 cycloaddition, and we are end up with this ones. Then dimers also can form, right? So the problem with these conditions is we can't control it. So the dimerize of this alkene alone can form, this alkene alone can form. So the dimer is 20%. So this is a 51%. Okay. Then the dimerization, this is cyclopentene. So this is dimerized as a 2 plus 2 cycloaddition. Cyclobutene also can undergo dimerization under photochemical condition. 2 plus 2 cycloaddition can happen. Then the bicyclic products also can lead to a new structures. It's an intramolecular cycloadditions. So once you are getting, if a closer proximity of two double bonds under photo conditions, that also the orbitals can overlap with each other, because suprafacial is allowed under photochemical, right? So this very strained molecule, even though it can form by the photochemical conditions. So this, then the cyclopropene things are very facile for the photochemical conditions because of the ring strain also. Okay. Now we are going to discuss about the same things with the 2 plus 2 cycloadditions. Anthropophile is allowed, but geometrically it is favored, right? Ketenes, we saw already, right? The ketenes are the exceptions in the thermal 2 plus 2 cycloadditions. So these reactions is facile when ketene bears electron withdrawing groups, and the ketonophile is the electron rich one. So this is a usual trend we are seeing. We are going to see in the Diels-Alder reaction. So now the electron withdrawing groups in the ketene. So what that happens is that will lower the energy of the LUMO of the ketone. Then the electron rich olefin have the higher energy HOMO. Now the energy, like now the overlap between the higher energy HOMO of a olefin and a lower energy LUMO of a ketone can happen easily. So under thermal conditions also we can make it favorable. So this is the one exception. So this is very minimized. So the interaction is more. Yes. So here this is a double bond of the C double bond O, right? So this p orbitals help the olefin to interact the carbon's p orbital by the anthropophile manner. That's why ketenes can undergo a 2 plus 2 cycloadditions under thermal conditions. Then the stereochemistry also will be retained. So what is the configuration here, which is a cis relationship with each other? This also has to be cis. So if a trans, then one can be above, one can be below. Now this is 2 plus 2 cycloaddition can happen. It will end up here. So the hetero double bonds also can be participate in the 2 plus 2 cycloadditions under thermal conditions. Okay. So this is a top angle view. So one of the orbital is approaching like this, one of the orbital is approaching like this. Now it's bonding. So this is a clear picture of how the anthropophile mode is. We should understand this one. So this is the excess case. So isocyanide also can participate in because of the double bond nature of this one. So these p orbitals is very helpful for the antrophysial interactions between a olefin and a ketene of it. Okay. So some examples. So this one, now this one of these double bond is coupled with the ketene by the thermal conditions. So now this is a base. It will pick one proton from here. Then here is the mechanism. So it's pick up proton from here. This bond is moving here. Then O minus. Then ketene forms. So this is a stable ketene with a dichloroketene. This dichloroketene now it can undergoes 2+2 cycloaddition with this double bond to give this. So if cyclopentadiene means it's giving this one. Okay. So this is also one more example. The 2+2 cycloaddition between this double bond and a dichloroketene. So here also dichloroketene will form. The condition is different thing. That's all. So zinc chloride will eliminate. Here zinc is a mediate to create the dichloride. So it's just creating a dichloroketene. Then the dichloroketene and a double bond will undergo cycloadditions. That's all. Okay. So this also actually this is a +2 cycloadditions. Here one point I want to add is you know already the nitro to keto. How there's a one famous naming reaction. Anyone known? Please answer this.
F reaction.
Yes, Neff reaction. There is so many questions nowadays it's asking from that. Okay, so these are also same things. So hetero double bonds also can participate in the 2+2 cycloadditions. Okay, now move to the 4+2 cycloadditions. It's well known Diels-Alder reaction. So many times you are get to know that there's Diels-Alder. Okay, this is a person Diels and Alder. They are getting Nobel Prize for this mechanism and discovery at 1950. Okay. The thermal cycloaddition reaction between cissoid conjugate diene and a dienophile using an olefin or acetyl usually. So form a 6-member cyclic compound is known as Diels-Alder reaction. So 6-member heterocyclic ring also can be synthesized from this one. The beauty of this is continuous formation of 4 chiral centers. So if you are seeing here, this is a simple example of the cycloadditions. Now this is also cycloaddition. Now disubstituted diene as well as disubstituted dienophile are undergoing cycloadditions. Now there is 4 substitution in a cyclohexane ring. 4 chiral centers we are creating in one step. That is a rapid step. So the reaction is highly regioselective and stereospecific. The first part is a diene. Correct? How the diene can be? It can be open chain or cyclic, but the main important point is a cissoid conformation. It's not a configuration, it's a conformation. So you should know the difference between these two. What is conformational isomers, configurational isomers. So yes, trans to S requires a very small energy barrier. So for a Diels-Alder one, permanent S is very extremely good because it's a permanent rigid S one. So it won't transfer to S trans anyway, which is extremely good. But rigid transoid. The transoid means the 2 terminal carbons of the dienes are away from each other. So there is no possibility of molecular orbitals can interact with the dienophile. So which is unreactive. If a bulky substitutions are present in a non-rigid transoid also, when you are turned to the cis side, it's forming some bulky steric things. So it automatically try to be a transoid. So that also is looking like a rigid transoid. So which also must be unreactive. So why? Because of the steric reasons. I will show you this. So for this one, these are completely cis, correct? With the rigid cis. It should be like this only. All of this can be like this only. So these all are very good for the Diels-Alder reaction. But these are a rigid transoid one. So this can't come closer to both of it. So this is not possible at all. So this is very unreactive. Once you are taking this one, so this is a conformation isomers, yes, because this is single bond rotation can be achieved this one. But the problem here is these two are very bulky substituents. When this tertiary butyl is coming here, it will form a steric interaction between these tertiary butyl. So it's automatically coming to this conformer. Now the Diels-Alder is very tricky. So that is only I'm explaining here also. So which is suitable, not suitable things. So first you are in problem 1. If any dienes are there, you should focus. It should be a cis or trans. That is the first point you should focus on. Okay, to the continuity. Cyclic conjugated dienes are more reactive due to the rigid cis conformation. Now these all are same cyclic conjugated dienes only, but when the ring of the size of the ring is increases, so the distance between the terminal carbons are increases rapidly, right? So cyclopentene case something closer. Cyclohexene it's a little elongated. So cycloheptene of course a broader. Cyclooctene also it's same like that. So overlap with the dienophile in a transition state decreases, so reactivity decreases. So now the cyclopentadiene is more reactive than the other cyclic cyclic compounds. Then cyclopentadiene is the most reactive, so it can undergo self-dimerization under room temperature. So if you are buying a bottle, then normal room temperature itself it form a dimers. So most of the cyclopentadiene will be dimer only. Okay, now dienophile. So alkene or acetyl is most of the time is a dienophile. So that should bearing electron withdrawing group, which is good because the electron deficiency of the double bond will be increased by the electron withdrawing group. So this causes the lowering of the LUMO energy level of the dienophile. So now the reactivity of the dienophile is increases because when you are decreasing the LUMO of the dienophile or you are increasing the HOMO of the diene, now the interaction between this HOMO and LUMO will be so much easier. So the electron withdrawing group is important because of the lowering the LUMO energy of the dienophile. Okay. So simple alkenes with conjugated carbonyls, these are examples. Carbonyls, nitro, nitriles, sulfones, aryl alkenes, vinyl ethers, and esters, haloalkenes are the good for the Diels-Alder reaction. Then the cyclopropene, I already stated that. Cyclopropene, substituted cyclopropenes, then cyclopropanones are the excellent dienophiles because of the high angle strain within the double bond. Because that is already a 120 degrees of cyclopropene, right? So the double bond also it's very strained double bond. So it's better to release that one so that it will easily undergo the Diels-Alder reactions. So cyclic alkynes are more reactive than the isolated alkyne. Trans alkenes also more reactive due to the angle strain. So the angle strain only is causing for the cyclic alkynes. So if a benzene is a cyclic alkyne, right? So that also is very facile for the Diels-Alder reactions because of the angle strains. Okay, then the product. So first diene, the dienophile, now the product. So now the look in the 6-member ring product. So the double bond is inside the ring and conjugated group outside the ring and opposite to the double bond. Okay, so this is the a typical Diels-Alder product. Now this is the newly formed double bond and this one is the newly formed single bond from a Diels-Alder. So when you are disconnected, like the retrosynthesis if you are doing, so start from here, then change the bonds accordingly, you will get this one. Okay. So this is the usual type of disconnecting of cyclohexene ring by the Diels-Alder things. Okay. So this is also recognition of Diels-Alder product. You already know it how it will be. It is of course a cyclic 6-member ring product. It bears one double bond. Then the electron withdrawing group, the dienophile having electron withdrawing group, is just opposite to the double bond. That's all. So this is a typical product of Diels-Alder things. Now I already told recently only. So, this is the HOMO of diene. It's the LUMO of diene. This is the HOMO of dienophile. Okay, just assume the dienophile and LUMO of diene. Okay. When the electron donating group if introduced in a diene, this HOMO level is increased. Okay, so HOMO level is increased. When a normal electron withdrawing group is attached to a dienophile, this LUMO level is decreased. So now this gap is very smaller, correct? So the actual picture is, if you can correlate these two, a simple diene, so HOMO of simple diene and LUMO of a dienophile, these two can interact with each other, or LUMO of a diene, HOMO of a dienophile, these two interact each other. But the energy between these two is very larger, but these two is comparatively smaller. So usually the HOMO of diene and the LUMO of a dienophile is taken into the account. But if you are introducing electron donating group to the diene, the HOMO is slight higher. Then electron withdrawing group, the dienophile, the LUMO is slight lower. Now you are getting better overlap than the normal usual overlap between a HOMO of a diene and LUMO of a dienophile. So this how the electronic effects happen into the molecular orbital things. Okay. Now we are see the product. Then the product also having some rules. So now the first rule is cis rule. Okay. According to the cis rule, the relative stereochemistry of the substituents in the 1,4 position of the diene and 1,2 position of the dienophile is retained due to the supra-supra interactions. Okay. What is retained means? I will tell you that. The trans and trans 1,4 dienes. Okay. We already saw this one. Is cis relations with each other after forming a bond. Okay, so first I'm taking this one. This is cis dimethyl malonate. This is cis isomer. So when you are forming a Diels order one, you are getting these two should be a same side. Okay, because you are getting a cis one, you are taking a cis one, you should get a cis one. It might be a top, it might be a bottom. That is not a problem because both are same only. So these two should be same side. If you are taking a trans configuration isomer, this is a configuration isomer, not a conformation isomer. Configuration isomer, then you should end up with a trans one. One should be above, one should be below. Okay, this is this thing. So cis trans. So I'm telling this is first this is a dienophile. Okay, this is a dienophile thing. So this is a cis dienophile cis relation. Yes, cis dienophile cis relation. Trans dienophile, it should be trans relation. Okay. So now it's come to the dienes. This one. Now the diene, this is a E isomer, correct? This is a E isomer and this is a E isomer. Both are trans isomers only. So trans isomer, if you are taking, then this should be cis relations with each other. So this phenyl ring and this phenyl ring should be same side. It might be a top or it may be bottom, that is not a problem, but both should be in same side because the stereochemistry will be retained. So if you are taking this one, it should retain as such. Okay, here also it shouldn't change. Here also it shouldn't change. Okay, because the orbital overlap diagram is showing here. It's a suprafacial addition. 4+2 suprafacial mode is very facile and allowed. Right? So if attaching like this, the trans one attaching like this, so you should get a trans things for this one, right? So this one, if you are the one more thing, the orbital diagram, this is a frontier orbital method. This is a orbital correlation method. So this one having a plane of symmetry, correct? So here on plane of symmetry is there. Then the product also should be have the plane of symmetry. Okay, if this trans one should not have means at the end also there is no symmetry will be there, correct? If you are having a plane like this, then these twos are opposite to each other. There is no relationship. Plane like relationship is not there. But there is a C2 axis is there this side. So this will come into the orbital diagram. But the point is the stereochemistry won't change. If there is a cis, it should be remain as a cis. If a trans, it should be trans. So here E isomer, trans isomers means it should be same side because this should be same side. But when one is Z, so this is a Z isomer, then this is a E isomer. So when you are having this type of two different isomers, then you should have it two different things. So one R should be above, one R should be below. So now there is no plane of symmetry. This is the C2 axis of symmetry only will come, right? So forget about symmetry also, but what the starting material if you are choosing, depending upon your product also can be, you can be determined, okay, this is the product because this is a configuration. So if the point is here, if that is a cis dienophile, you are getting a cis relation. Trans dienophile, a trans relation. If that is a trans-trans isomer, you are getting same side cis relations. If that is a trans-cis isomers, you are getting a trans relations. That's all from this slide. This is a cis rule. The main one word is stereochemistry should be retained. There is no change in the stereochemistry because of the suprafacial interactions between the dienophile and the diene. Okay. Now the endo rule. The approach of the dienophile can be endo or exo, correct? If for better understanding, exo is above, endo is below. Okay. In the endo approach, allow maximum spatial overlap of the unsaturated diene and a dienophile. So this one. So this is a diene one. Is a dienophile one. So when it's coming below, there is a maximum spatial overlap. So this is the secondary orbital one. So this is the frontier orbitals. So what we are seeing till now is frontier orbitals of a diene and frontier orbitals of dienophiles are interacting each other and forming a bond coming to the 6-member rings. So this is a one more extra step. The secondary orbitals interactions between a dienophile and a diene, which favors the endo product in a transition state. Okay. Actually, exoadactus is thermodynamically stable product, but endo is forming in why? Because of the kinetically stable endo transition state is formed because of the secondary orbital interactions. Okay, here it's the same one. So this is the endo one, less stable, however predominates. This is the exo one. So this is a more stable one. Under this is a thermodynamically controlled product, means this is a more stable one, but the kinetically, energetically more stable endo transition state is attained by the secondary orbital interactions. So endo project is predominates than the exo one. Okay. So this is a for better understanding the red bond here is frontier orbitals are approach each other. Then the blue bonds are backside bonds. So additional secondary orbital interactions, which is a kinetically favored transition state. But this one is a front to front only coming, means there is no secondary orbital interactions. This is a exo product. So these will end up with the exo product and this is the endo product. But the kinetically favored transition state is the endo one. That's why we are getting endo things more. This is a dimerization of cyclopentadiene. So that also endo product, not the exo, because of the interactions between these double bond and these double bonds. Okay. Now, when the temperature is -10, you are getting endo higher products. When you are increasing the temperature from -10 to 170, so when 120, the endo products is decreasing, but exo is increasing. So at 170 degree, you are getting only 40 endo, 60 exo. Why? Because this is thermodynamically controlled product is exo. So when you are increasing the temperature, you are populating the thermodynamically favored products. So which means exo one. So but under lower temperature, the kinetic control is more. So endo is the kinetic controlled product. So you are getting endo more at lower temperatures. Okay. Now the next part is the regioselectivity. So the formation of regioisomers is depends upon the relative variance of the molecular orbitals. Symmetrical diene or dienophile, there is same size of molecular orbitals. Unsymmetrically, you substituted the diene or dienophile. So you are getting a different size molecular orbitals at the end, which means at the terminal carbons. What we saw earlier, the electron donating groups, when we are substitute to the dienes, you are getting a higher energy homo to get the better interactions. You are getting these terminal molecular orbital in a bigger size, a larger size, for example, because it's the electron donating one. Okay, when you are coming to the dienophile, because of the electron withdrawing group here, you are getting the terminal carbon bearing the molecular orbital should be large and it should be positive, slightly positive. Okay, so both of the terminals should be larger. One, the electron donating one should be slightly negative. Electron withdrawing dienophile should be slightly positive. Now these two can interact better than other side. And the major product is ortho one. Actually, we shouldn't use this word ortho. But for our understanding, I'm keeping ortho or meta. Okay, the major product is ortho product. So, okay, this is a terminal substitution case. If next the second carbon or third carbon is having a substitution, now this terminal is a bigger molecular orbital having a negative charge because the electron donating nature of the substituent. But there is no difference in the dienophile because electron withdrawing group is there. This carbon only having a plus charge, a slight plus, not a plus charge, slight plus charge. Now these two can overlap each other better than other two. So now you are getting major product is as a para. Okay, because this one is a is the second carbon having a substitution of the electron donating group, not the first carbon. So this should be para as a major because of the orbital interactions. So this is a screenshot from Glyden that also explains the same what I explained now. So X is the electron donating group. Z is the electron withdrawing group. So these are all examples of electron withdrawing groups. Okay. Now regioselectivity. This is a double bond between carbon and oxygen. These also can undergo a 4+2 cycloaddition to give a pyranone systems. So this also one more example having a nitroso one. This also is a dienophile. So this can participate in a heterocyclic one. So why dienophile only having a hetero part? Dienes also can have. So it's alpha beta unsaturated part. But these also having involved in the cycloadditions to give the pyrone rings. Okay, the side selectivity. So if you are taking this double bond also can participate as a dienophile. This double bond also can. But this is a more electron withdrawing group is there, right? The cyano also there, the keto also there. Cyano also there, the keto also there. So this is more electron. So this LUMO energy having much lower energy than the other things. So first this should undergo. Then if excess equivalent of diene is there, this side also can be possible. Okay. Intermolecular wise also it's possible. If the proper arrangement of a diene and a dienophile can come to the closer proximity, you are getting a 4+2 cycloids product in both the manner, like chair-like transition state and a boat-like transition state you are getting. So here the point is the secondary orbital thing is not possible because it's already connected. Every bonds are connected. So normal steric considerations only importance than the Endo rule. Okay, solvent effect. Actually, Diels-Alder reactions, there is no need of solvent because there is no ionic intermediate, right? There is no ionic intermediate, only a transition state. So actually no need. But when water is introduced in that, the rate is very effective in the Diels-Alder things. Then the endo exoselectivity also is more for the endo thing than the exo. So this is a report they gave from the water is good accelerating agent, accelerating solvent for the Diels-Alder reactions. Okay. Then the rate controlled by the lowest HOMO and LUMO separation attained by the diene and dienophile partners. The structural and electronic factors lowers the magnitude of HOMO and LUMO separation. So this is a formal normal electron demand Diels-Alder. Diene having an electron donating group. Dienes having electron donating group raise the HOMO energy level. So LUMO compared to the LUMO of the unsubstituted one. So if the rising will help us for the interactions between the other things. Like if a HOMO is rising, then the LUMO of the dienophile can be interaction easier. So the same thing. The dienophile bears electron withdrawing group. lowers the homo energy. So electron donating group higher the homo energy, electron withdrawing group lowers the homo energy. In inverse one, completely reverse. That's all. So here diene bears electron donating group, but here diene bears electron withdrawing group. Here dienophile having electron withdrawing group, here dienophile having electron donating group. Just inverse electron demand, so it's inverse Diels-Harder reaction. This is a combined slides of the things. So thermal conditions 2 plus 2 forbidden, photochemical only allowed, but 4 plus 2 thermally allowed, photochemically forbidden. Diene having electron donating group, dieno having electron withdrawing group is good under normal conditions. Then major product should be endo because that is a kinetically controlled one. Then stereochemistry should be retained. Okay, stereochemistry should be retained. As a regiochemistry wise, ortho and para is good than the meta. Okay, this is an endo product, how it will be. If you are taking a EE isomer, you should get cis isomer. EZ isomer, you are getting a trans isomer. Once you are getting a dienophile as a cis one, the relationship is cis. That is a trans one, the relationship is trans. Then this is the ortho para, slightly negative, slightly positive. Okay, so that's all. Thank you so much.